We all good? Good morning, welcome everyone. My aim this morning is to share some slides with you, talk a little bit about power transformers, and hopefully one or two of the slides out of the many I have will give you a little bit of interest. First of all, background, Doble Engineering, the company I've worked for overall for almost 9 years. It's based in America, has been in business since about 1920, it's almost 100 years now. We have a large conference each year in Boston. We have about 1,500 people turn up, mainly clients. And we've just had our 81st, that's 81st successive annual conference. First one was 1934. We don't own transformers, we don't make transformers, well, not really anyway. We don't fix them, we don't repair them, we don't maintain them. But we'll tell you if your transformer's gone wrong. We'll tell you what you need to do, how soon you need to do it. So just to get out of the usual rut, here's a picture of a transformer. The one on the left is a nice orange color, it's out in the desert. The one on the right has just been tested because it was hit by a bridge on the way to site, just being transported. Concept of an intelligent monitor is lost somewhat if, on the right, if you're transporting a transformer and you have solar-powered impact recorders, and then you put that transformer in the hold of a ship where it's dark. So that transformer had several days worth of travel where we didn't know what happened to it. Small transformers, they found on poles. This is the other end of the scale on the distribution side. And in California, we grow our own transformers. We have transformer farms. Inside, they're complicated. You can just see outside all around the place pictures of transformers. They are complicated devices and they will fail relatively easily if you know what to do. In California recently, a year ago now, there were a bunch of transformers taken out of service by some snipers, terrorists. That one is still being investigated. We've seen pipe bombs on substations. These are external causes of transformer issues. Sometimes those external causes can be how you put the transformer together. So this is a transformer, very small, it's pole mounted, it's got its own little set of bushings. There's a transformer on the right, it's got its own little conservator. Problem is, it doesn't matter how clever you make the transformer, if you then encase it in an operational network where you've got no idea what's happening to it or when, or who attached wires to it, you're going to have a problem making sense of the data. But ultimately, a transformer is relatively simple. Just in the background, let's look at asset management. One of the key title words was asset management. In Google, there is a tool you can use, and that Google tool will allow you to look for the occurrence of a word in the literature over the last 500 years. And we can see that the word asset really started being used in about 1900, about 110, 115 years ago. Asset management is the red line on the same scale. The number of times it occurs in the literature is very, very small and really has only started in the last 10 years. So asset management is really just growing. We've had assets for hundreds of years, we've managed them for hundreds of years. Asset management is the skill, the discipline of making sense of it. ISO 55000 is an international standards organization standard for asset management, published in January of 2014, this year. It was based on the previous standard, PAS 55. This standard tells you what an asset is. Anything that can bring value to your organization. It's up to you to decide what value that is. And asset management is just a coordinated activity of bringing that value out. So asset management doesn't just cover maintenance, doesn't just cover operations. It includes transformer specification, purchase, bidding, operation, maintenance, disposal, and so on. Throughout PAS 55, throughout ISO 55000, there's a common theme, and that theme is risk. What are the risks to the transformer? And risks need two things. First of all, they need a hazard, what might go wrong, and then you need to have an idea of when that might happen and what will consequently result. So here's a 345 kV station. This is just northwest of Boston in Massachusetts. And it's a fairly big station, got some big transformers. You see off to the top right, you can picture this on Google Earth. Off to the top right, there are some interconnections. Those are coming from the DC station next door. That's a 2,000 megawatt dual pole DC station, which is almost 1,000 miles long. Comes down from northern Ontario. That's a big station that provides a lot of power into the New England system. And in the blackout of 2003, which was begun by some trees in Chicago area in the Midwest, this was the reason the lights in New England stayed on. That and some guys in the operations center who didn't like the fact that the blackouts in the Midwest were starting to domino effect and cascade across. This is a very important station. It's a big risk. If it fails, if a transformer fails, the consequence will be huge. Financial, customer minutes interrupted, customers interrupted, reputation. So we need to look after those assets, and in particular the transformers. If we don't plan effectively, then we are not effectively planning. If you don't plan for failure, then you're failing to plan, is the old phrase. What's wrong with this circuit breaker? This circuit breaker would have been in slightly better condition if someone hadn't tried to re-energize it after it had failed. This may seem like a ridiculously small thing. There is a control room, they're looking to see if they can re-energize a breaker. They're told it's okay, R210 can go back in, they switch it in. The wrong people have been looking at this. That put 11 kV back on the control wires, sent the energy back into the control room, burst all of the controls, and you've got flying glass across the control room. Unexpected consequence of a failure. You have to think in terms of what might happen and will result. An intelligent approach will make sure that you don't put that back in service unless you've actually done a proper visual. You need trained people. And if there's one thing that comes out of this talk, is that it's knowledge. Someone somewhere has to know what they're doing. Someone has to know what's going on. Excuse me, sir, could you click on the Life of a Transformer seminar for me? This is some slides. Each year Doble runs a Life of a Transformer seminar. And we run this as a course. It's 5 days. This particular one is a number of years old. I've taken a couple of slides from an old buddy of mine, Jin Sim, who runs a thing, how do you make a transformer? And the point about this is that you're winding coils. I would imagine at a coil winding and industry expo that a lot of people know about this. Quite often people don't. And the important thing about coil winding is that you're still using the same techniques, and we're still applying those same techniques from a long time ago. Could you click on the video? So this is a movie from Westinghouse. This is 110 years ago. If you want to get a copy of the movie, you can download it from the Library of Congress, which is a United States website. On the left, you have drums of wire being wrapped into transformer winding. On the right, you have the same approach, big coils of wire. It hasn't really changed that much. The basics of a transformer are the same as Faraday would have recognized 160, 70 years ago. Copper, paper, oil, steel. We have improvements in the way things are done. So in this video, it's one of several from the Westinghouse works. You can see one, it's all the women who do the work. And two, we have asset managers. They're the ones who wander around looking to make sure everything is done correctly by the women who are actually doing the work. Okay, that's enough of that one, thank you. So if you just escape out of that. The life expectancy of a power transformer, IEEE. IEEE will give you that at full load, a standard transformer should last 180,000 hours, 20.55 years. Peter, could I get... Sorry, it rained, so all of my moisture is external at the moment. I'll just take it. This is an interesting slide. As one, most transformers are not loaded to 100% of the time. And two, we're based on a hotspot calculation. And the hotspot you don't measure 100% correctly, you measure with an estimation. So most of our calculations about the actual aging of a transformer are an estimate. We don't know the true hotspot. We don't know exactly how precise that value is, and we don't know how long it's been at that temperature. But if we have an estimate, we can then say what the degree of polymerization should be at the end of life and how long our transformer's got left to live. So what we find is people talk about 180,000 hours of life, and you can work out how many years, months, days your transformer's got left. The interesting thing is, people will give those numbers in terms of 3 years, 6 months, 4 weeks, 2 days, 7 hours, 5 minutes, and 28 seconds. But the degree of accuracy is plus or minus years, and the degree of precision is similar. So you have to be careful. But why do transformers fail? How many actually fail because they've just reached end of life? It's very few. This is based on it's a different company. This is based on Hartford Steam Boiler. A gentleman called Bill Bartley. He presents papers when he was working for Hartford Steam. Why did transformers fail according to the information that his clients gave him? Important thing, look at the top 3 causes. Electrical disturbances outside of the transformer. Other causes outside the transformer, lightning. Those 3 main causes account for 2/3 of failures. And those 3 main causes are external to the transformer. Now it does get complicated because the older a transformer is, the less likely it is, because of the aging, to withstand an external fault. But 2/3 of the problems are externally caused. Vandalism, lightning, other sources. Our intelligent condition monitoring is not necessarily going to address those causes. So if you have a transformer, think in terms of how we're going to look at all the different sources. If, however, you look at those failures, and remember those failures are based on what people say. These are insurance claims. Insurance claims are supposed to be exact truth. They aren't always exact truth. You can put a curve on that, and you'll see this as a survivor curve. A survivor curve tells you what the likelihood of failure is and how many of the population should have failed by a certain age. And Bill Bartley and his colleagues put together a formula. Your challenge in conversation today is to use the phrase modified Perks formula, which is what this is. I never knew there was a Perks formula. But what you often see with this type of graph, this type of chart, is a nice curve, a nice increasing failure rate. Unfortunately, real life isn't necessarily like that. 2 things. 1, what are the accuracy and precision? What are the error bars on those measurements? They're huge. So we have to be very careful about using these things. But it does say, based on his information, that about half your transformers should have failed by the time they're 40 years old. In my experience with Doble, and we've looked at thousands of failures around the world, that's not the case. On the basis of his results in 1999, Bill Bartley presented a paper at Doble saying, in 2008, there will be a huge rise in failures and the world will not be able to build enough power transformers. So we went to see him in 2011 and said, you need to rewrite the paper because it didn't happen. So he rewrote the paper. 12 years on, he's moved the date back 12 years. So now predicting in 2022, there will be a huge rise in failure rates and we won't be able to cope. But if you compare this, based on information he's got, and look at an actual population, this is the number of the number of transformers installed at a utility. The orange is distribution, the blue is transmission by year. And you have transformers going back over 100 years. There's one from 1907, there's ones from 1920, the ones from 1928. They're big transformers and they work fine. Have they gone past their IEEE sell-by date? Yes. Do they still work? Yes. Do they need replacing? No. I was the asset manager who helped put the strategy together to deal with these. You don't need to replace these because they're old, and you don't need to replace them because they've seen a lot of life. They were built to withstand it. So a lot of these transformers from the old times will still be there in 100 years' time. unless you have those 2/3 of external causes, lightning, vandalism, system faults. But even then, they're built big. So what we found was that the probability of failure during the first 70 years starts high and fades away. It's the start of a bathtub curve. And the likelihood is, by the time you get to the bottom of the bathtub curve, random failures will just take over and you won't see the far end. But we're seeing 60, 70, 80-year-old transformers, and the failure rate for that population is not increasing. Is it worth putting monitoring on those transformers? Probably not. How much do you need to know about a transformer that has sat there for 80 years doing its job? How much more can you learn about that transformer? Probably very little. But the interesting thing is, as Marsh, as HSB, as Aegis, other insurance companies will tell you, the transformer is a very small part of the insurance loss. It's the business interruption. So we're interested in transformers and their failure because it may take out the generator station, may take out chemical plant. It's that dollar consequence which is huge. If that transformer looks okay, unfortunately it's failed. I'm just on the left-hand side of the tank. You can see me looking at it, putting my hand on the tank and saying, do you feel okay? Because it's very difficult to tell. You take the windings out from the transformer, very complicated device, that's a failed transformer. That one was repaired, put back in the tank, put back in service. That was actually identified using about 3 or 4 different techniques. The exciting currents gave a problem, turns ratio gave a problem, winding resistance, SFRA, a whole bunch of different things gave a problem. And you have to put all that information together to try and identify the cause to see if it's worth taking to the factory to take it out and fix it, because it all costs money. This transformer hasn't failed. It's the same transformer. It still has not failed. It was pushed. It didn't fail. Something else damaged it. So you have to be very careful about failure statistics. And now the consequence is going to be, is there any oil from the transformer in the river? That's going to be a cleanup cost, which the company is liable for. And in the UK, in Europe, not the transportation company, the owners of the transformer are liable. Standard transformer fire. If you do things right on a substation, you can build cable trays between transformers to allow all the cables to be connected. You often find snakes and small animals. In this case, one transformer failed. It's the one on the left. And it failed because a snake crawled up the bushing, caused a flashover, bushing failed, transformer followed. Oil from that failure went into the cable tray, moved along to the next transformer, took that transformer out. One snake took out 4 transformers. It's in Arizona. How much condition monitoring do people sell for snakes? Do you have a snake monitor? I put this one here because they've marked the marked the windings so that when they've taken them out, they can put them back in the correct order. Internal failure modes, coking on tap changes, overheating of windings at particular design spots. Lightning, if the lightning levels go up, you will have an increase in failures because you have more faults on the system. If you have animals contacting snakes, squirrels, birds, they too will cause problems. Someone drives a car into your substation, that can be a disaster for the driver, but also for yourself. And then you have lightning. I think that's staged, it's a Hollywood movie, but it gives you the idea. If you look on YouTube, there are pictures that people have taken while driving along, and they happen to see lightning hit a pole-top transformer. Those are available for download. It's quite spectacular. What monitoring do we do for lightning? We can pick that up. But the question is, where's the intelligence? If I'm going to have a smart grid, I want to put that intelligence so my transformer is protected and the business it serves is protected. So part of the intelligence is, do you justify a decision? So in this case, I'm making a decision. On the left side, I have a transformer, it's been damaged. Do I replace it or do I fix it? Simple decision. In this case, it's false that you should replace it, and it's true that you should refurbish it or fix it. The nice thing about this approach, it's a decision tree, is that you can put prices, you can put dollars against the different outcomes, and you can put probabilities. So we've identified that the chance of a new one failing is 1% at $1 million, and the chance of a refurbished unit failing is 5%. You can then work out the expected monetary value of your decision, and you should refurbish. People like spreadsheets, and this is just spreadsheets. You can take the level of analysis one stage further, and you can do this in real time, continuously, looking at all of the available data. What happens if we add in that the failure may be catastrophic, and now we don't just have the cost of a new transformer, we have the cost of the cleanup, and the cleanup could be $10 million. The last large cleanup I came across in North America was at Indian Point, just north of Manhattan. That was a transformer that failed. It was a $20 million US cleanup cost, PCBs in the East River. But now you've got the ability to say there is a huge possible cost implication, but there's only a small chance if it does fail. So we've got to do contingent probabilities. Humans are not very good at probabilities at all. But really you've got replace, refurbish. If it refurbish and it fails and it's catastrophic, that's probability of A given B. What is the cost? But it's still true you should refurbish. But you can upset that because the refurbished decision is made on site. We'll take the transformer, we'll take it back to the factory, we'll check it out and we'll fix it. There is a chance, new bottom line, that it's not in fact repairable. Just a small chance, say 1 in 20, 1 in 30. You add that in, and now the decision to refurbish is no good. You need to get a new one. As part of an asset management system, ISO 55000, this is the kind of thing which is the start of a decision to replace or refurbish. If you want to make an intelligent decision, you need intelligent data, and you need to have tools which justify the decision, so someone can come along and audit it. So a little bit on condition monitoring. 3 C's. Control, context, conclusion. You have to control the measurement. That doesn't mean we over-control. There's no point in making a temperature measurement to 4 decimal places on a power transformer. We don't need the ambient temperature to 2 decimal places. It's not useful. Understand the context of the measurement. If you're making a measurement, you have to know, did the transformer trip out? Did I take it out for maintenance? Have I used this with lots of through faults? What's the context of the decision? And when you make a decision, it has to be a conclusion which is actionable. People don't understand quite often that you can either do nothing by default, which is ignoring it, or you can decide, you can do nothing by design. You have to have an actionable conclusion, an intervention. Let me give some examples. There's a paper from guys in Australia at the 80th conference we had, 2013, and we're looking at bushings. Why monitor bushings? Monitor bushings because they fail. In the picture on the right, you can see the bushing on the right failed. The bushing in the middle, which has been taken apart, it did not fail. It was killed by something else, which is the bushing next to it failing, and the explosion which took out that one destroyed the center phase. Could you do me a click on the left and the right? Just one click on each, please. So the video on the left is very, very quick when it happens. That's a bushing failure. How much monitoring would you need on this substation on the left to be able to detect a bushing fail? You could sit there for 50 years seeing nothing. There has to be a cost benefit to justify that failure being identified. On the right, you've got a bushing at an oil circuit breaker. Again, you could sit there with a lot of monitoring for a lot of time, but when that bushing fails and it takes a circuit breaker out, there is a big consequence. The main cost of this could be just purely reputational and stock price. But there's a lot of interest in these things. How would condition monitoring help with those things? You can measure the leakage current through the bushings. Relatively easy to do. You'd expect the leakage current through the bushing to be the same on all three phases and to be about the same size. Unfortunately, it doesn't matter how well you control the actual measurement, in reality it's not like that. You have to understand the context. The system voltage changes, bushings may not be the same. They have different capacitances. These are real leakage currents, and those leakage currents are not sinusoids, they're not equal magnitude, and they're not 120 degrees apart. But this is what you have to get used to. Over time, you can derive from that information what you'd hope is a nice, graceful indicator of a bushing failure. And this is looking at the power factor over several months. And this gives you time to bring in the spare bushing, to look around. Intelligent monitoring on the transformer. Someone has to have a plan. Because sometimes it doesn't act over months, it takes 2 hours. It's no point after 1 hour saying, what do we do? The intelligence has to be recorded, written down, made available. And in this case, the operations guys on a transmission system, and trying to change a transmission system is like trying to steer a battleship. It's a big, slow thing. Once the alarm came in from the bushing monitor, they had 2 minutes to take the transformer out of service, which they did. And in the investigation, they realized that there was a lot of damage to that bushing, and it would have taken the transformer out. One of the tests for transformer integrity is SFRA, sweep frequency response. It tells you about the mechanical integrity of a transformer. And we can look at the coil and the response, and we can see how they change over time. SFRA is a very, very good tool for detecting movement. It's also a very good tool to detect people who are not very good at field testing because they get the results wrong. We take a coil, we measure it, it's in green. You add the core. If you look at the green trace, it's just a pure inductance. It's what you expect. As you get to higher frequencies, as capacitances kick in, and you get a different response. The one in black is when you've added a core. That's a 3-phase unit. You can tell because of the low frequency response. There are 2 resonances around about 2 kilohertz, 1 kilohertz. Take that coil, dry it out. Does it make much of a difference? No. SFRA recently has had technical papers where people say you can measure the moisture in your transformer. Well, you can under ideal conditions, but I wouldn't use it in the real world because there are so many other things which have such a far greater effect that the moisture is neither here nor there. You add oil, you get a different result. You dry and clamp, you get a different result. You add oil. There's lots and lots of variation. What is best to have is a reference. So these are actual valid results that you can use in the factory. There used to be a guy, Jim Fivey, up at Transformer Manufacturer in Edinburgh, and he would use SFRA in the factory as the coils were moved around to check to see if there's any movement or damage. And it works. But you need someone who knows what they're doing. Take, for example, a low frequency response. In this kind of area, that's heavily dominated by the core. It has an expected shape. That will change as the core relaxes. And the core will get to a point which is lowest total energy, lowest action. And as it relaxes, the frequency response will change. When you go and test this on site later, it's going to look different. And that's because you're measuring between 2 points, and those 2 points are electrically connected capacitively, inductively, to the whole transformer. And so you're testing everything between those 2 points. This is Dr. Mark Lachman from Doble, and he does a lot of work on this because he used to work as the Delta Star Chief Test Engineer. So how about those as SFRA results in the factory? Do they look okay? All those who agree, please raise one hand. So, not big on X-far. Okay. They look fine. They're a fingerprint. They look okay. If you know what you're doing, you can tell it's a three-phase. You can tell which phase is which. You know it has the expected shape. It looks like you'd expect. There are differences at high frequency. It may be due to asymmetry in the design. It may be due to some grounding variation. In the factory and in the field, are these acceptable? When you know that one's with oil and one's without oil, you've changed the capacitance, the resonant frequency due to the LC combination is shifted, they're acceptable. What about these three? Sorry, these two. These two are, again, field and factory, same kind of situation. Are they acceptable? Yes, they are. You can make a decision. So this is a small mobile unit. It was taken out of service. It had some gassing. It had various things going on. It's not often I get people invading the stage, but Peter's allowed. This transformer was taken out of service. Golden rule, if you took it out, it goes back in. There has to be a really good reason if you have taken a transformer out of service that it doesn't go back in. In this case, there's a lot of variation between the phases. But what you have to do is say the data in the SFRA here tells me there's a shorter turn on that transformer. No other test really showed that. And when you look at the nameplate, there's enough information there to allow you to make an actionable conclusion. And the conclusion is it goes back in service. And the reason for that is during testing, someone's identified a tertiary winding. Can anyone see the tertiary winding on that transformer? It's not obvious. Just up here, there are outlets from a power outlet winding that powers a substation electricity, powers control unit. If you short one of those, it provides a short circuit. So this is about context. Someone somewhere has to know what's going on. And as a lot of data comes in from an online monitoring system by the millisecond with a SCADA system. And when I worked at a North American utility, 50% of our stations had no SCADA. Let that sink in. If we wanted to find out that there was something wrong at the substation, we had to wait till someone rang in and said, my lights have gone out. Red and yellow. Red, bad, yellow, good. Where do we look? We look at the places where it's red. You don't need to be 100% focused on your transformers or your intelligence system 100% of the time. As a background, as an individual, how much information are you as a person taking in second by second? The answer is about 1.5 gigabytes. You're only aware of about a few megabytes. So what you need is a system which will allow you to focus on your top concern and tell you what the ranking is, what the impact will be if this is out financially, and what the likelihood of that is. And the way we look at that is to start and say we're interested in the assets, asset management. What we have are lots of data sources. And what people try and do is link the two. Don't do it directly, it doesn't make sense. You need analytics, which will tell you when the data has changed. And you need to use those to address failure modes. If the data doesn't address a failure mode, ask the question why you collect it. Those can be grouped into an assessment. Those assessments will then tell you about a logical part of the transformer. And the data has to have a relevance. So we can look at one particular transformer and say green good, yellow bad, blue we're not too sure of. But you need to be able to bring all of the data together to give you a risk score. Because you may make the decision that this transformer is in a poor condition, but we'll let it fail. That's a decision which you can make, which we have made. Actively letting a transformer fail. 99.999% of people in your organization don't care about this level of data, but someone should. And the reason they should is that the computer system won't tell you everything, and someone has to know what's going on. Microgrids are where we started. Pearl Street, Southern Manhattan, 1877, 1876. They're microgrids. They grew and they expanded. The industry is now going through really its first iteration, its first 100+ years, and that's its first life cycle. Microgrids are where we're heading back to, but each microgrid needs support, whether it's wind power, solar power, whatever else. I will always come back to the third line. We still need people who know what they're doing. Otherwise, we're always going to pay extra for that ability to be ignorant. As a thought, how many people have heard of the Titanic? Titanic, a big ship. Kate and Leo, 1996, movie, Oscars. A lot of people died, as a result of which, put lifeboats on all transformers based on the number of people, not based on the number of tons the ship is. How many people have heard of the SS Eastland? There it is. It rolled over at the dock in Chicago. It was already top heavy. You add more stuff to it, it rolled over. For those who went to the CWIEME in Chicago, you can go see the plaque. 847 people died. No movie. So you have to be careful. I will always come back to the very simple point. Someone has to know what they're doing. And with that, Peter, apologies for delay. It's all yours. Thank you.
Well, thank you very much, Tony. Tremendous amount of information there, and I love disaster movies, so I especially was delighted to see that. Probably time for one or two questions, if anyone's got one or two.
If anybody wants copies of any of the slides, let me know and I can share them out.
Yeah. Well, you can all go and rent or download your Titanic film now, I'm sure, knowing a bit more about transformer disasters. So thanks again, Tony.